So we just finished up talking about queues, and specifically a linked queue implementation. Again, we need to make sure we're keeping in mind that the implementation and what a queue is are separate ideas. All I care about with the queue is that I can in-queue something, de-queue something, get the first, and all those extra little things we talked about. That's it. None of that, how I want to use a queue, tells me about how it's actually implemented. Remember that. If it sounds like I'm beating that dead horse, it's an important dead horse to beat, because we have to keep those ideas separate. People will come to office hours and they get hung up on these things, and that's fine, you're learning these things, but that's why I want to make sure I'm emphasizing it enough that we get it. So, last time when we had a queue, what was the, okay, so we had a linked queue, right? We had, let's say here was like the head, and we'll just talk about kind of like this general case. We're not too worried about those edge cases for what we're going to talk about right now. And we had, I guess we kept track of the count, we kept track of the front, which was a pointer to the front, and we had the tail, which is a pointer to the tail. Do remember that front and tail, they're pointers. They're not the actual nodes. They're not what the nodes are holding on to. They're just pointers that can get us to the node that we care about. So this is just trying to recap what happened last week. When I in-queue something, where should it go with this linked implementation?
Last.
Here, right? And when we de-queue something, where should it go?
From first.
Exactly. We take it away from the first. So now that we have more officially talked about the computational complexity, what is the computational complexity, if this is our situation, of adding something to this queue? 1. That's what you're saying, 1. Why 1?
Every time it is getting added to the last, I mean, there is no shifting.
Yeah, there's no shifting. Exactly. That's basically 100% right. All we do is always just go to, okay, tail, set your next to the new thing, update tail. Like, that's it. In the general case. Edge cases aside. But even with edge cases, it's still simple. Basically, the question, we could reframe that question to be, does the length of this queue, like let's say there are n nodes in this queue, n things in this queue, does the amount of time it takes to add something to that queue in any way depend on how large n is? No. Exactly, because we always have a pointer to the last thing. There could be a bajillion things in between here. And at the end of the day, all it's going to be is create a new node, set this one, set tails next to the new node, set tail to the new node, we're done. So it's an order 1 operation to dequeue, which is pretty cool. That's pretty handy. What about, wait, no, dequeue. That was queuing. Yeah, queuing. Pardon me. Did I mess that up the whole time? No, it was only that last time. Hopefully. Anyways, let's say I'm dequeuing now. So within queuing, we've established it's 1. It's like nothing. It's constant time. It does not matter how many things are in that queue. How about when I dequeue? What's the complexity of that? Say it with more courage.
1.
That was not very courageous. One more time.
1.
Okay, all right. I'll have to accept that. It's order 1. Complexity is 1. Why? Well, all I have to do is take whatever the data is out and set front to be this next thing. That's it. That's all we have. We've got deleting and whatnot, but those are all easy little operations. Again, I can reframe that question as, let's say there's a bajillion things in this queue. Does that matter? Does that change how long this takes? Let's say there's 5 bajillion things in this queue. Does it matter? No. So it's still constant time. So every time we in-queue, it's constant time, and every time we de-queue, it's constant time. That's pretty good. Like, we're pretty pretty happy about that. I mean, I suppose when we think about this, the linked stack, it was basically the same, right? It was always order 1. All the action was happening at the top. Okay, cool. So with this queue, we've got order 1, with this linked implementation. So that's awesome. So today, we're going to talk about array queues. So just like a stack, how we did the linked stack, and we had the array stack, well here we've got the linked queue. We could also build a queue with an array. Why not? So let's take a moment and think about how we would want to implement the idea of a queue with an array. The whole lecture is going to be about this. But before we even start talking about it, I want to give you a chance to think about how on earth could you implement a queue with an array? And the answer is there's a lot of ways you could do that. But try to come up with a good one, whatever that means. So honestly, take a couple minutes, talk amongst yourselves, try to formulate an idea of how you would keep track of all that information. You know, we can use the linked implementation as a starting point. Right, okay, so that's what we did linked-wise. How can we do it with an array? Go, chat, take a couple minutes. Think about this. Okay, let's just start talking about some potential ideas. Rate, this is just a poll. I'm not looking for answers at this stage. Raise your hand if you think, yeah, I can totally implement it. Raise your hand really high, I want to see. So, a chunk of the class, okay, good. No, wait, not that confident in your idea? No, okay. So how about this? Let's start with this idea. It's a simple idea, it will totally work. Here's what we can do. We'll have our array. Let's pretend it's arbitrarily long. We might have to expand capacity every once in a while, but we've got our array. And here's what I'll do. Why don't we just make the front 0, right? So I don't even need to keep track of, oh, where's the front? It's 0. So front, it's 0, it's always 0. And the tail, we could do it kind of like the stack, where the tail is like the next available spot, I guess. So if this is our queue, like A, B, C, tail might be 0, 1, 2, 3. And I guess we could have some sort of counter as well. Although I guess we don't even really need that, because we already know if tail's 3, how many things are in that queue. Yeah, that's pretty easy. So how about this is our situation? Let's talk about this. I want to be very clear, this implementation will work. There's nothing wrong with this implementation. It'll work. But, well, one moment. So, here we are. If I want to add something, where do I put it? 3, tail. Okay. Right, this gets updated. You know, maybe I need to expand capacity, and if I do that, how long does that take? Order n, it's linear because we have to copy over all the contents. But we do amortize that so we can kind of pretend that doesn't exist, but we'll just keep that in the back of our heads. So in Q, in general, is going to be what operation? Without thinking about expanding capacity, operation. What's the time complexity? 1. Why? Well, you just put it in the next spot. That's it. I don't care how long this is. The length, the size n of this Q has no bearing on how long it takes to add something, I guess. So that's pretty cool. So the in Q for the linked implementation was order 1, and the in Q for this array implementation is order 1. Perfect. Let's talk about DQ. So here's what we'll do. If we want to remove something, we'll just remove it, and then we'll just shift everything down, right? Well, this will have to go here, this will have to go here, this will have to go here, and so on until we're done. Yeah?
Could you also shift?
Well, no, don't worry. What? I like the way you're thinking, but how long will this take? Why n? If there are n things in that queue, and I have to shift them all down, I gotta shift all n things, it's linear time. Not horrible, but definitely worse than order 1 that we had with the linked implementation. So, although this implementation will 100% work, the problem is, this implementation, the way we're doing it, it's a lot worse in terms of like computational complexity. This is where computational complexity becomes really important. There's this weird growing phenomenon, especially with people who are, and this is not intended to come across elitist in any way, shape, or form, but a lot of people who are informally educated in programming, they won't learn about computational complexity. And not having that framework to kind of analyze our decision making could be problematic, because if this is the array implementation, it's not. And we saw the linked implementation, which of the two should you always use? Linked, right? Ignoring engineering things about how those computer boxes are working in front of you, of course. You should always pick that, the linked implementation, because this is bad. So knowing about computational complexity allows you to ask the questions, what's better? You know, thinking about the amount of work these algorithms are doing. That's a very important concept. So, okay, I've got a really simple solution for fixing this. In the sense that, when I say fix, I mean improve its computational complexity. How about what I do, instead of shifting them down, I just keep track of where the front is. Right? So now, okay, front will become 1. So now if I want to DQ, I just go to index 1, I'm good to go. So now, what is the computational complexity of DQ? What? 1. It's 1. Fantastic. Suddenly we've improved this. Simple, tiny little change. Suddenly I don't need to do any shifting. We save a lot of work. Can anybody see a potential, I don't want to say problem, but thing that we might want to be aware of? What do you think?
The original front being lost and creating a memory leak.
That is a potential issue, but let's say we're good programmers and we didn't have that issue. Oh, although, in a sense, you kind of actually got the right answer, I guess, because at the end of the day, this chunk of RAM with our array implementation is kind of left, I think it's always going to be empty. So it's not a memory leak in the sense that we forgot to delete something. We have this memory issue where we've got this cell in an array that it exists, but it's always going to be empty. Because well, here's the front. The front, like if we're not shifting anything down, the front's only going to move this way, and we're going to lose this ramp as we go down. And then, like, this end is going to grow pretty quickly. And then we're probably going to have to call expand capacity a bunch more times. Like, imagine we were using this implementation, and I've got an array, and I've done a bunch of InQs and DQs, and I've DQ'd a bunch. And I've got like A, B, there's like 2 things left in my queue. All this RAM though, it's like useless. We've lost it. So that chunk of the array is forever left to be nothing. And yeah, we're just gonna grow really rapidly that way. So, okay, like, and on one hand, we've made a really big improvement, right? Like, we reduced the computational complexity of DQ from n to 1. Fantastic. But it doesn't seem to have solved all our problems. Raise your hand if either of those 2 ideas were the ideas you were talking about. Really high, I want to see. Okay, good. You're normal. Really good. But there's a third idea, the good one. Does anybody have any idea, and if you've looked ahead in the slides, I don't want you to answer, does anyone have any idea on how we might be able to improve this? What do you think?
Could you delete the spot that is now empty and then turn F into 1?
You're not wrong, but I'm feeling you're wrong, if that makes sense. Any other ideas? What if? You know what? No, I'll make you wait for the surprise once we get there in the slides. I gotta, make this class interesting, right? Okie dokie. So, yeah, the queue implementation with an array implementation of a queue. So we need a container, let's use an array. We need something to keep track of the front, an index. Maybe we need something to keep track of the end, another index, keep track of the size, probably some integer, or if we're just fancy, if we know the tail is basically the end, we can just use that information. But here's idea 1. This is the first idea we looked at. Have the front be index 0, keep track of the rear, and then every time, so AQ is array Q. Here's our idea. I guess in this scenario, we only need 2 attributes. Oh yeah.
When you have to keep count of the rear, like let's say we expand capacity, usually we do like ×2. Wouldn't that screw it up? Because then like the index would be like way back.
No, the index will stay remember the difference between rear and max. The max size doubles, but index won't double. The rear won't double. It just always gets added 2 by 1. Yeah.
In regards to the Steam third implementation.
I don't want to hear your idea about that.
And no more? Okay.
Yeah, no. Ship has sailed.
Okay.
The esteemed third implementation. I like that phrasing. I'm going to use that. So here we only have 2 attributes, Q, which is the array, and rear. Because if we already know that the front is 0, then we don't need to keep track of that. And if rear is always going to be the next available spot, based on 0-based indexing, we could easily know the size. So that's a pretty nice condensed implementation. So AQ, if I InQ something, we add it to the end, we DQ, we have to shift everything down. Of course, that shift is going to be a linear time operation. Not horrible, but absolutely worse than constant if you can get away with constant. So, okay, so will this implementation work? Yes. Will we have to expand capacity? Yeah. What is the complexity of InQing? It's the same. Yeah.
Why would you have to expand capacity if you're always removing anyways, so it's everything shuffled down?
Well, because let's say I have 10 things in that queue, right? And my max array size is 20. And then I say in Q 11 more times, but I never DQ, right? So it could just keep growing, and we're gonna have to expand capacity. What is the complexity of DQ? Linear, because that's shifting. Rats. So here's the second idea. We already talked about this. Have an index keep track of the front, rear, and we'll just do this. And we'll just kind of like shuffle on down. What is this implementation? Okay, is it going to work? Yeah. Do you have span capacity? Yeah. What is the complexity of in-queuing? It's still 1. De-queuing, 1. How often will we call expand capacity relative to idea 1, do you think? More? Yeah, I suppose, because we're not shifting, so it'll probably have to do that a little bit more. We're wasting that space. So idea 1 versus 2. Okay, which would you prefer? Can we think of another implementation? Well, now let's talk about that esteemed third implementation. So here's what we're going to do. It's effectively idea 2 with a clever twist. And I hope that you're going to be kicking yourself that you didn't think of this brilliant idea. Because it's simple, but it's brilliant. And those are often the most fun ideas, right? The simple, brilliant ones. So here's what we're going to do. Index to keep track of the front, 1 to keep track of the rear. And here's what we're going to do. If we ever get to the end, just go back to the beginning. We'll remember the fact that the front might be index 7, and the rear might be index 2 or something. But we'll just loop around. Now, obviously, our array is linear, right? But we could think of our array as like a circle, kind of. Like, think of it like this. Bear with me while I draw a circle. So this is index 0, 1, 2, 3, 4, 5, 6. What comes after 0? You think 1. What comes after 1?
2,
What comes after 2?
3,
What comes after 3?
4,
What comes after 4?
5,
What comes after 5?
6,
Here's the big one. What comes after 6?
0. 0.
0. Why? Because that's our rule. Once we get to the end, we go back to 0. Do you remember 2 classes ago, I think, when I said, okay, what comes after A? What comes after B?
C,
What comes after X?
Y,
Y?
X, Y,
Oh, Z. You meant Z. Oh, sorry. Oh. What comes after Z? A. Oh, you just go back to, oh, okay. It's the same, we're just going to go back to the beginning. We can think of them as like this like circle. It doesn't have to be linear. We can think of it as a circle. So that's all we're going to do. So just 1 second. So if I've got, and here's what I've got, my empty cube. Okay, so I've got, okay, I in QA, I in QB, I in QC, I DQA, I in QA again, I guess. Then I put a D, oh, and then I'm going to DQ, 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 E, F, DQ, A again, maybe G now, H, we'll DQ. Right now, what index is the front?
3, 6,
6. Yeah. What index is the rear?
2,
I mean, 3. I guess it depends, right? Are we doing the next available spot or that? But yeah, it's one of these two at least, depending on how we implement it. We'll just loop back around. What were you going to say?
Oh, it's just that like with a circle like that, it's just like there's no. It's hard to visualize an endpoint.
Yeah, there is no endpoint.
So okay.
Of course, yeah.
How would you expand capacity?
I guess that's going to be I mean, obviously that's a good question because the following could happen. W, X, Y. Where do I put Z? Put it after 6. What? But, I don't know, what am I don't know. We'll talk about expanding capacity in a couple slides. Other questions? I thought I saw another hand somewhere.
I had the same question.
Okay, well, I like the way you're thinking. Let's get rid of this ugly picture. So we'll have a circular array. It's not actually a special type of array. It's just a regular old array, but we pretend it's a circle. The array is really linear. It starts at one and ends at the other, but we can pretend that it loops back on itself. Yeah, okay. If the index what index comes after n? 0. Well, I guess maybe n minus 1, but the index that comes before 0 is n, or n minus 1, depending on how you really are counting. The index that comes after 0 is 1. So yeah, I mean, I already showed you this, right? We could just, just keep going and just updating like I did before. So we could have something like this. We'll have our Q. We've got an index that keeps track of front. It's just an integer. One that keeps track of rear. And we'll have a count, although I suppose we could just do the difference between the front and the rear, but whatever. And that's our situation. So far, so good. But of course, there's that burning question, how on earth are we going to expand capacity? So, yeah. So, okay, but it seems like it's going to be complicated, all this bookkeeping required. No, it's actually easy. Actually, we'll get to expand capacity in a moment. I guess I got to show you the magic math to give you an easy way to loop back to the beginning. Actually, does anyone know of an operator that might come in handy here? We have.
Is it push?
Nope. It's a simple mathematical operator we've used in programming before. It's fine if you don't remember because it was obscure and we only used it in like 2 places before. Last chance. Any thoughts? All right. Anyways, that one. Remember that? What's it called? Exactly. Okay. Let's just think about this math for a second. People see this and they start thinking, oh, what the heck was that again? I don't remember. No. Take it easy. It's simple. You're thinking too hard. Classic just starting computer scientists. Remember, one of the most important things you can learn as a computer scientist is don't think too hard. So, we did mod 2 before, right? And what was mod 2 helpful for? Even or odd, right? So if I give you the number 0, mod 2, what's the answer?
0.
0. Say 1.
Well, is 1 true?
No. We would check. If it's a yes, but that's not what we're checking here. We're not getting a Boolean. This gives us 0. Why? Well, because how many times can we get 2 out of 0?
0.
What's the remainder?
0.
0, okay. 1 mod 2. How many times can we get 2 out of 1?
0 times.
0. What's the remainder?
1.
1. So 0, 1. Now here's the trick. How many times can we get 2 out of 2?
2 times. Sorry, 1.
1 time.
1 times.
1 time. What's the remainder?
0.
Oh, okay, yeah. Notice that as soon as we ask like a multiple of the 2, it's just going to become 0. It just goes back to 0. Okay. Let's pretend we have an array of size 10 or something. So if the array is size 10, that's its max size. Right now, rear is 8. Okay? So the indices that exist in this array are 0 through 9. Okay? Now, let's say I in-Q something. What should rear become? 9, right? This should become 9. I mean, put simply, rear should be like r equals r plus 1. Right? There's nothing new here. But of course, if I ask the question, what should rear become? Now, after like, okay, rear is now 9. And I do this, what would rear become? 10. Which of course is problematic, right? Because there's no such thing as index 10. What should it have become? 0. Huh. Based on what we just saw with the 2, what could we add to this little expression here?
Mod n.
Mod,
N, how many? N
like
minus 1.
max, I guess. That's what you think. Mod max. Where in our case max was 10. So, let's go back in time. Here, we're at 8. Let's do the expression. Okay. R equals, okay, what's R plus 1? 9. What's 9 mod 10 in our scenario? How many times can we get 10 out of 9? 0. What's the remainder?
9.
Oh, we're good. Okay, cool. It's 9. Which, oh, that's convenient. I in Q. What's R plus 1?
10.
10. What is 10 mod 10? How many times can I get 10 out of 10?
1.
1. What's the remainder?
0.
0. Oh, okay. So rear becomes 0. Let's say in Q again. What's R plus 1?
1.
0 plus 1. 1. What's 1 mod 10? How many times can I get 10 out of 1?
0.
What's the remainder?
1.
Oh, okay, so this becomes 1. We'll do it one more time. What's R plus 1?
2.
2. How many times can I get 10 out of 2?
0.
0. What's the remainder?
2.
Oh, okay. Now we'll do one more. Let's pretend it's 9 again. Alright, so we did it all that time. What's 9 plus 1? How many times can I get 10 out of 10?
1.
What's the remainder?
0.
Oh, okay, yeah. It just keeps looping back. Yeah. Isn't that amazing? Yeah.
It makes sense, but isn't that kind of pointless if you want to keep track of everything if it's overriding everything all the time? Like,
Well,
if
it's not overriding anything because we might still have to expand capacity. Going back to your question. We haven't talked about that yet.
Oh, okay.
Because this is assuming that there's like space left. So mod, you remember it's the fancy thing that basically means, gives you the remainder. What's 4 mod 2?
0.
Why?
2
Because
times
it is. Because it's a multiple of 2. Well, how many times can I get 2 out of 4?
2.
2. What's the remainder?
0.
Yeah. How many times can I get 4 to 5? What's the remainder? Yeah. How many times can I get 8 out of 7?
0.
What's the remainder?
7.
Perfect. Okay, so it's really handy for figuring out something is easily, yeah, we've already done this. Like, check if something's evenly divisible by 2. Is it even or odd with mod? Easy. And so on. So here's what we're going to do. Here is our rear and front update expression. It's just rear equals rear plus 1 mod capacity. Here I wrote it as max, whatever. Same thing. That's it. Basically just keep adding 1, but if we ever get to the end, just start back over at 0. Mod makes it really easy to do that. Who here thinks that's cool? Yeah, that's what I thought. Who here thinks that this idea of looping back is clever? Put up your hands. Yeah. Yeah, it is. See, it is clever, isn't it? Oh, it's brilliantly simple, but clever and beautiful. If that doesn't get you excited about computer science, there's something wrong with you. So here's the situation. Okay, so we need the special expression for updating the rear. Do we need it for the front? Yeah. Can this ever run out of room in the array?
Yes.
I'm looking at you.
Yes.
Yeah, of course it can, right? We might be in big trouble. So we might have to expand capacity because let's say this is my cube. I add something. Okay, great, we're fine. The front is 2 and the rear is 2. Everything's still fine. Everything fits perfectly. But if we try to enqueue anything, we're going to be in big trouble. So here's what we want to do. We'll create an array that's bigger. These locations, so front is 2, right? So we can expand the capacity and copy everything over. But if I left front as 2 and rear as 2, let's say I dequeue. So I eliminate that blue box. Then I dequeue again and I eliminate 3. I mean, what comes after 3? 4. It's like I've got a hole in the middle of my circle. So we can't just simply double the size and copy everything over without getting very creative. Well, my battery's running low. How much is left? I'll lower the brightness. Hopefully my computer will end at the end of this class. So this, not a good idea, because I want to make sure I was being clear. What comes after this? This. What comes after this? Well, that, but really, if I were to ask that question, rear equals rear plus 1 mod max, it would want to go there. So this is like a giant gap in our queue. Because if 2 is the front, and then 3 comes after, suddenly I've got this giant gap, and then I have, and then the 0 and the 1. Do you kind of see what I mean? Seeing a lot of blank faces. I don't know if that's a good thing or a bad thing. Seeing more nodding. Okay, it's a good thing. So here's what we could copy it over and have it in the middle like that. But what I like to do is double the size and then copy the front of the old one and put it in index 0. Then the next one, put it in index 1. Then the next one, put it in index, and so on. So the new queue will start the new queue. It's the same queue, but the new array, that's the container, will start with the front being at 0. Does that make sense? Yeah? It's a simple idea, but it'll work. It's glorious, yeah.
So you're basically like pulling everything back.
Kind of. It would be like if I have that 2, 3, it's just I don't have the colors to draw those boxes, but it's like, okay, 2 is the front, here's my old one. Let's just do A, B, C, D. Okay? Now I want a bigger one. Good. If I copy just C, D, A, B over, that's problematic because then that's not good. But what I'll do is I'm like, okay, A, you're the front, right? Because I know that front is index 2. So you go there. B, C, D, I'm good. That's the idea. Other questions about it?
So it
Yeah.
will be dequeuing from that initial queue and then enqueuing to the new.
Nope. After we've done the expand capacity, all enqueuing and dequeuing will be done on the new array. That's the container. So, will this implementation work? Say yes. What is the complexity of enqueuing? 1 plus expand capacity might be a thing. What is the complexity of dequeuing? 1. Do we have that weird wasting RAM issue? No, we don't have that weird running off expand capacity issue as well. Hey, nice. So, yeah. What a wonderful implementation. So, because my laptop's about to die, I guess we'll do a lecture activity. And you'll have a lot of time to do it.